Okay. Well, no Eva, so we'll see what happens there. Okay. Are there any questions on the homework that I need to address? Anybody have any questions on the homework? Okay. I'm not hearing anything, so I'm assuming nobody has any questions. Okay, we're gonna move on. Before we move on, just a quick note. It looks like we're going to get our first quiz next Thursday. Our first quiz will be between 1.1 to 1.4, I believe. With 1.3. 1.3. So 1.1 to 1.3, we will have a quiz on Thursday. That'll be an in-class quiz, obviously. Okay? So I'll go from there. All right, 1.2, functions and graphs. Let's move on. Functions and graphs. Functions and graphs. What do we need to do about functions and graphs? We have functions, so we have a set of bunch of x's here. And we're going to connect the x's with a y, and this is the function. We call the function where you have a x and it goes to the y. So that's why the x is called the what? Anybody? What is the x called here?
Domain.
Okay, it's a domain. All possible x's are called the domain. Okay, that's a good thing. What do we call the x? It is something variable.
Oh.
It's the independent variable, right? And the y varies depending on the x, so we call this the dependent variable. A little stroll through memory lane in algebra. We talked about this in algebra, right? Independent variable versus dependent variable, right? So this is the domain. All possible x's go to the y. What are the all possible y's called? Not the domain. What is it?
Range.
Range. Okay, so we have domain, which is all possible x's, and then we have the range, which is the all possible y values, right? Domain and the range, right? Domain and the range, okay? Incidentally, this notation, f of x, was done by who? It was done by the guy on the picture on page 13, bottom left. Who is this guy? Anybody have their book open?
Leonhard Euler.
Oh. Leonhard Euler, not Euler, Euler, okay. Anybody know why it's pronounced Euler? This is the guy's German, right? The German enunciation is Euler, okay, not Euler. The same reason why we pronounce this as what? How do you pronounce this guy's name?
Back.
Bach, right? Bach. Bach. You don't call this Bach, right? You don't talk about Bach's concerto, right? It's Bach's concerto. Same thing. Euler, not Euler. One of my pet peeves. Okay. So that's that. Let's go to example number 1. Write a formula that expresses the area of a circle as a function of its radius. Use the formula to find the area of the circle of radius of 2 inches. Okay, well, this is pretty tough. Area of a circle. Area of a circle is equal to what? Pi r squared, right? And when r is equal to 2 inches, A is going to be equal to 4 pi square inches, right? Because I have multiplied inches twice here, inches squared. Okay. Domain and range. We talked about domain and range. Domain is all possible x's. The range is all possible y's. If you go to the middle of page 14, there's a thing called the implied domain, or also what is known as the relevant domain. Okay? These are domains that are sometimes not specifically, if it's specifically notated and it's shown, okay, it is called the relevant domain, okay, or a restricted domain, it's a relevant domain. In other words, if I said, let's see, we have a function that looks like this. 9t plus 50. Okay, and I gave you t is greater than that, then this is a relevant or restricted domain because I'm looking for t, but only between 2 and 5. Okay? If I took this away, and I told you, does anybody know what this formula is for? Anybody have a guess? Does this look familiar to anybody? This does not look familiar to any of you guys?
It does, but
Parabola.
we don't remember.
Huh?
Parabola.
Okay, it's a parabola. But what is this specifically? Does anybody know? Remember we talked about the
Throwing a rock.
there you go, throwing a rock, right? You're going to throw a rock. So you're going to go from here, you're going to throw a rock from a height of 50, and you're going to throw it up, and it's going to go like this, right? Okay. So if I told you this function is the height of the rock, there is an implied domain here, right? The implied domain is what? Even though it's not shown here, what is the restriction on the domain? Time has to be greater than 0, right? You cannot have negative time, correct? So you have this implied domain, okay? All right, this is an example of an implied domain. Okay. So bottom of page 14, there was something about boundary points, interior points, closed intervals, open intervals, right? So if I had a domain, again, that looked like this, is this an open domain or a closed domain? This is a closed domain because both of the endpoints are included here, okay? That's why it's a closed domain. If it looked like this, it would be an open domain because the endpoints are not included, okay? So if I go like this, all right, this could also be notated as this, right? Included. If they were not included, if they were open, it would look like this, correct? All right, okay. Again, this is stuff that we've already done before. We're kind of going over it again. So that's the difference between open and closed boundaries. Okay, let's go to example number 2. Identifying domain and range of a function, okay? If I ask you what is the domain or the range of a function, one of the ways to do it is just look it up on the calculator, right? So let's go to A. Identify the domain and range of the function. A, so this is example 2A, where y is equal to 1 over x. And if I draw that out, it's going to look like this. Okay? Okay. So the x-axis is the what here? Can anybody tell me what the x-axis here is called in this instance? What's this called? It is a point where the graph tries to get to, but never gets to. Tries to get there, but never does. What is it called? This ring a bell? It's an asymptote. It's an asymptote. So the x-axis would be a horizontal asymptote, whereas the y-axis here is also an asymptote because it tries to get there, but it never does. It's a vertical asymptote here. Okay. So what is the domain here? What are the all possible x's? Anybody tell me?
Everything but 0.
Everything but 0. So it is all numbers except for that, right? All reals except for that, right? Or in other words, you can just write this too. X is not equal to 0. What about the range? All possible y's here, right? Except, so all the y can be everything except for what?
0.
Y cannot be 0, right? Because it's a horizontal asymptote. Y, you try to go to 0, but it never gets to 0. You try to go to 0, but it never gets to 0, right? So everything but y equals to 0, not y equals 0. Everything but that is the domain. I mean the range, right? So that would be that. In B, we're going to talk about y is equal to root x. If I graph that, it looks like this. Okay, so what is the domain here? Natalie, what's the domain? Natalie? Hello, Natalie, are you there?
Sorry.
Huh?
Um,
Are you there, Natalie?
yeah.
You are? Okay, so what's the domain here? All possible x values. What is the domain here in this?
0 to infinity.
What?
0 to infinity.
Correct. So x has to be greater than or equal to 0, correct?
Yes.
Okay, good. What about the range? What about y?
Zero to,
It actually goes all the way to infinity, okay?
I don't know if it's,
Again, so y is greater than or equal to 0, right? Okay? So that's what that would look like. Okay, so that's that. Flip the page. Let's go to example number 3. Example number 3. Example number 3. Use a grapher to identify the domain and the range. Then draw a graph of the function. Use a grapher, use a calculator to graph to identify the domain of the range. Okay, the domain of the range. So, what is the first one? Y is equal to x squared. Put this in the calculator and you draw it, you're going to end up with something that looks like that. Okay, so this is A. Example 3, is it? Example 3, okay, all right, A. So what is the domain of this? What What is the domain of this, Caden?
-2, 2.
So -2 to 2, correct? X can be between -2 and 2, right?
Mm-hmm.
That's the all possible x's. What about the range?
0 to 2.
0 to 2, exactly. Right? Because from the y direction goes from 0 all the way up to 2. Good work. B, y is equal to x to the 2/3 power. If you graph this, you're going to end up with something that looks like this. Okay. So the domain here is what? Luke, what's the domain?
All numbers. Right?
Yep. So the range is all reals, correct? I mean, the domain is all reals, right? What about the range?
Greater than 0.
Correct. Y is greater than or equal to 0, right? Good work. Okay, evens and odd functions. We talked about this before. An even function. Give me an example of an even function, anybody? This is the most common one. Y is equal to x squared, right? It's an even function. How can I tell it's an even function? An even function is symmetrical across the y-axis, correct. Also, an even function satisfies this relationship. So where x is, if I put a negative x, it has the same value. So I can verify this by, if I had where x is, I put negative x, right? It would be like this, right? Y would be equal to this. This is the same as x squared. So this is f of minus x, where x is, I put minus. It's the same as f of x. So f of x is the same as f of minus x. So it's an even function. Okay? All right? All even functions are symmetrical across the y-axis. Anybody else give me an example of another even function? Possibly something we learned second semester last year. In trigonometry, there's any trig functions that you know that's symmetrical across the y-axis maybe?
Cosine.
Cosine, right?
I was supposed to
Cosine.
say that.
Goes like this. So y is equal to cosine x, right? It is symmetrical across the y-axis because y is equal to f of x is cosine x. F of negative x is, I'm going to put negative x here, so cosine of negative x, cosine x. Hang on a second. Okay, so y is equal to cosine x is a even function, all right? That's an even function. Odd function is what? Odd function is no longer across the y-axis, but it is now symmetrical across the what? Odd function is sine x.
Origin.
It is, again, yes, it is symmetrical across the origin, right? An odd function is symmetrical across the origin and across the origin, right? And also, y is equal to f of minus x is no longer f of x, but it is minus f of x. Okay, this is how you would algebraically prove that it's an odd function. Okay. Let's go to example number 4, recognizing even and odd functions. Y f of x equal to x squared is an even function. Okay, we already talked about that. We did that. F of x equal to x squared plus 1 would be the same thing, right? Because all you're doing is just raising the function up 1. So it is still going to be symmetrical across the y-axis. Odd function, f is equal to x. Okay. But if you put the plus 1 on there, it is not going to be any longer an odd function because now it is not. If I go from y is equal to f of x, and y is equal to x, I initially have this, and yes, this is symmetrical across the origin. But if I go x plus 1, what do I get? My graph now becomes this, right? This graph is no longer symmetrical across the origin, correct? So this is no longer an odd function. Okay. So we'll stop right here. And for the first half of day